So great. I wanted to start a little bit on, we're just the first of all the sessions today, and we're talking at the QPU scale. And the QPU by itself is already, and we all have unique challenges based off our respective companies. But in addition to powering that QPU, we also need a hardware infrastructure to start to support that. And we saw a couple of slides where you're saying, here's what we have today, here's the commercial available stuff that we have, and we're going to keep scaling down and keep integrating. So I just wanted to maybe just to kick us off a little bit, can you start there in terms of the challenges of sort of having your own things where you have hardware infrastructure for your QPUs, and then from there we'll transition into sort of the business side of it. So maybe we'll start right at the end with you, Alex.
Yeah, I mean, that's a broad question.
Yeah.
I think that the industry is still pretty nascent, and one of the things that we've seen is that there's a lot of work that we need to do on guiding our partners for developing new technologies, and particularly adopting the kinds of developments that they've already had for other industries into what we're doing right now. In our case, I'm thinking a lot about laser systems, about optics. We have some very specific requirements for what these systems need to do for us in terms of the quality of the light that comes out, the power, how the optics needs to handle this power. And the reality is that there is a very mature industry for lasers, for optics, but it's been optimized for something completely different. So you can find very high-powered lasers that, for the types of applications that I think about, and I try to think like an atom. These lasers are effectively light bulbs. They do not have any kind of coherence. So if we want to really expand the capabilities of the quantum computers that we're building, we need to work at the source on kind of keeping as much of that controlling quantumness from every single component that we have. A lot of the work that we're doing is still advancing the capabilities as fast as we can, and that doesn't always have to come together with focusing on, for example, the size of the systems that we're building. So we are focused on how do we build better systems, and we will figure out how to miniaturize things in the future. But particularly for the kinds of processors that we're building, we have infrastructure requirements that we don't see really growing with the number of qubits that we control. When we think about power consumption, when we think about cooling, we see scalability in our approach, in that to go to double the number of qubits that we have, we don't need to just build another system next to it and figure out how to connect it. I would say that that's not even scalable. That's extensible, but not scalable. So we are focused on answering the questions of how do we partner with the technology suppliers to make sure that we can get to these millions of qubits in a single processor that, at least in its first iteration, is effectively the same size and almost the same power requirement as the systems that we are building today.
Great. Owen, you want to comment? Do you have anything to add?
Yeah, absolutely. I think I'll pick up the thread a bit with sort of the suppliers and working with partners. So the parallel that we have is we use dilution refrigerators to achieve the superconducting environments. Those units are very impressive. But they've largely been built for an academic market. So the people who've developed those aren't yet thinking about how they're going to build those into data centers, what the form factor needs to be, all of the aspects that you would need to achieve in order to have better compliance with data centers. So the chilled water is one example. Data centers do have cooling, but they don't have the cooling requirements that you typically would want for a cryogenic unit. So what we have to do is go back to the manufacturers and work with them, sometimes from the ground up, in how do we develop the next generation of fridges with the right form factors. It's not just the form factors. The other thing is they're built for experimentation. If the experiment goes down or fails, that's largely acceptable. An experiment's interrupted. A small number of people are affected by that. But once you start thinking about, where quantum computing will eventually go, that's a much bigger problem. So we want to have much better diagnostics for these units. We want to control the maintenance cycles. We want to make sure the redundant power's there. We want to make sure, we have ample cooling. So these are things we have to work with the suppliers on. I think the other element of this is maybe on the HPC side. Again, we don't quite know where this is going. We don't know all of the compute that we need in order to run these systems. At OQC, we're not yet using error correction. We will eventually need to go in that direction. So we don't know what the requirements of those things are. I just think it's a fair bet to say that first of all, you're going to want to co-locate that equipment right next to your QPU. You won't want to pay the network penalties. We've been quite happy with some of the data center environments, actually, because we can achieve these L2 network connections, and then therefore we get very low network variability. We've also don't have to worry about, we know what the cage power requirements are, so we can work towards them. We can expand outside the cage, or we can go to another data center in the metro if we need to. And yeah, we can also work the same way against the cooling requirements. So, in labs, we typically find that we get to a point where we can no longer exhaust the heat from the HPC side of things. So these are the angles that we're typically thinking about.
Yeah, great.
Yeah.
Joshua, what do you think?
Yeah, maybe I'll just, I think they covered a lot of the points that I was going to say, but, I'll just emphasize that co-design is a big part of our strategy. Yeah. So working closely with our strategic partners like Infineon, also bringing in other groups from like NIST and Sandia, and really to, have a collaborative environment where we're designing what we need internally, but we're also thinking about once we get to scale, how we're going to mass produce these systems. And so we really see that as key. To really first start with the basic science, but also we're thinking about what is the ecosystem going to look like in 2030, and what are the challenges we'll have then when we really want to mass produce these systems. The other thing we are thinking about, and I used to work at NIST, so I do like standards, is what does the interface look like to our system? And I think one thing that would help the industry is to align on standards. For instance, like what is the interconnect to your system? Is it QIR or CASM? Or so really making a uniform interface that application vendors can build off of, I think would be another thing that we're thinking about, just in terms of scaling in the future.
Perfect. Yeah, and I want to dive into that a little bit more after we hear from Stephan. What do you think, sir?
I just want to pick up two aspects. The one that Josh just mentioned, so I was lucky to be able to witness this already a couple of times. These co-design workshops, there's really powerful acceleration and innovation going on. And then the second is what you mentioned, that many come from academic startups. So that is in my short talk, I also mentioned we are like an outlier a little bit. Not many of other large tech companies outside of the big hyperscalers, right, are engaging here, which is for us particularly is good, but overall I think is slowing it down a little, that not more large corporations are embracing quantum so far to help bring all the infrastructure that is needed to bring this to market and to life.
Yeah, and for my next question, I want to start with you again, Stephan, because Infineon, you have so much history and expertise in just the semiconductor world. I guess sort of we call it the pre-quantum semiconductor world. You have a lot of expertise, a lot of technical mastery in the space. To go back to what Joshua was saying on standards, right now when we talk to so many quantum startups, kind of the key challenges, there are cost challenges at the startup side, where there's just everything is bespoke, so we have very high unit costs. And because of that, the capacity is limited because there's just not a lot of suppliers making the thing. And if you do, then your customer number 200 in line to your vendor. And then all of those things are further compounded that the supply chain risks are then very challenging, because then you could be single sourced for this one very critical component that your whole business is sort of banking on, but you're single sourced. And we found that some of our single sources are themselves single sourced, which is a really rough way to build a business plan. So can you talk a little bit about how you're thinking about the cost structures of where we are today, how that's important to scaling, and maybe from Infineon, can you go backwards in time? You're very good at scaling large. Looking backwards, what would you like to see in quantum?
I don't know if I can really answer your question.
Yeah.
I just want, for us, it's really strange.
Yeah.
Right? We are used to making millions of chips, right? And now it is about what, 100 or 1,000 of quantum computers that we will build each year or something in 2035 or 2040. Maybe the networking communication side can help here a bit with higher unit counts, but still, it's right now it's about enablement, and I want to, maybe you can pick this up. I want to throw this out there.
Yeah.
Are we already in the phase where you should think too much about second source? This is a race for every of these companies on stage. This is a race to build the first meaningful machines. I think it's going to likely be a winner takes a lot or a winner takes most scenario in the end of the first quantum computers that outperform all the others. And in that race, maybe, did they have second source for everything when they went to the moon? I don't know. Maybe you need something single that works first.
Yep.
Yeah. I mean, that is what I was saying, right? Like, I think that miniaturization, all of that, like, we'll get to that, but the very first challenge that we have is, can we build a market that can sustain itself? I mean, we see a lot of activity in quantum computing, but this is, like, I think beyond early adopters. We're just trying to figure out, how do we start thinking about quantum computers? But this can only last so long. It really is a race to show that we can do something that is unique and differentiated. And we have seen from history that, costs come down once the market starts appearing. And I don't think that the market for quantum computing right now is, sustainable in and of itself. I think that really it is a healthy combination of hope and fear. Hope for what we will be able to do.
Optimistic
fear
pessimism.
That, exactly.
Yeah.
But that is how we see it, and I think that it is important to have, a as much of a diversified supply chain as possible. But there's really, especially for for startups, there's only so much that we can do, right? Like we are, for the quantum computing stack, we may be somewhat vertically integrated, but the reality is that we're always going to rely on external vendors for the underlying technologies.
Yeah.
And working with vendors to guide their own development and making sure that we're not single threading, and also encouraging new companies to come out and start solving the problems that we have in our supply chain, and creating a stronger ecosystem, and also thinking now about economic development in the different geographies that we're present. I think that is going to be very important. But all of that is with the explicit purpose of getting to utility as quickly as possible, because that's what we all need.
Yeah, fantastic. Yeah.
Yeah, I'll add to that as well. I think one thing that we need to provide for the suppliers is the forecastability. And I think something that we often find with our suppliers is they need to, in order to achieve more reasonable unit costs, they're going to want to know what next year is going to look like for them, or the next quarter. One thing that we saw sort of anecdotally, is that when we were deploying our original quantum computers to data centers, we actually disrupted the global supply of a particular grade of coax cable.
Yeah.
And we only found out about this because some of our competitors started complaining, we can't get this stuff anymore. I think you guys have brought it all up.
Yeah.
You know, those are the kinds of things we'd like to try and avoid doing, because ultimately it would drive the cost down. And we need to have, you know, whether it's multiple source or single source, you need to be able to obtain this stuff and make sure that it's sort of built to the right quality as well. So for us, it's the forecastability. I think the other bit is educating the supply chain and enabling them to do the validation for us.
Yeah.
So something that they rely quite heavily on us is that to the right tolerance. Now, if the tolerance checks require you to have a dilution fridge, you're going to need the expertise in running the dilution fridge to be able to do those checks. So, you know, ultimately we're taking a lot of the burden of that on, but ultimately we want to be able to push that further into the supply chain to make sure that they can sort of certify it and validate it. And again, we get back to standards here, but I think that's where you end up going.
Yeah, that part is what I think, talking to the most of industry right now, everyone agrees that for these items that are considered IP and competitive advantage of the different quantum companies, way too early. It makes no sense to standardize any of that, because, you know, today, by next year, your version 2 could already be obsolete. So totally agree. And so I love the coax cable example, because how far can we go below on that IP stack that now you have cables, you have, we spoke a lot at dinner yesterday, lasers, things that are commonly available, but not quite usable without you doing additional quantumification, which is also time and labor and additional costs. And so that we can approach that utility, how can we take care of these smaller pain points? And maybe standards is one possible way. But do you want to say any couple more things on standards or interfaces?
I'll just say that I agree with what everyone said here, is that the first challenge is getting to a workable fault-tolerant system. Completely agree. We do look at second sourcing where appropriate, but a lot of times we're building one-of-a-kind unique things. And so really there it's working closely with those vendors. We do look at, as we go from system to system, how we can make things more efficient. So certainly that is part of our process, is looking at manufacturability from one generation to the next, so that when we do get to the final system, we have something that is scalable. And so we're not building ourselves into a non-scalable solution.
Okay. So to pull that thread on scalability, so, you know, we've sort of introduced the topic at QP level. We've talked about some of the infrastructure needed to grow. There's a lot of discussion in our community these days about sort of quantum HPC hybrid solutions as part of both the R&D side on just how to build a better QPU, as well as how to scale up to, you know, this eventual data center level of capability. Where do you see, and if you're able to share a little bit about your business, where you see that sort of hybrid quantum approach today and how it's helping your businesses as part of the scaling journey? And any of you,
Maybe I'll
Sure, yeah.
So we see it kind of on both fronts. So one is integrating like at the application level, where there are examples of where you can distribute workloads between HPC and quantum systems. For one example might be where you have some sort of chemical, you have a very large chemical and a small part of that is highly entangled. You can send the highly entangled part to the QPU, the larger infrastructure to the HPC, and you can use those in tandem to end up with a ground state calculation. So we see integration at the application level. We also look at integration for HPC in the actual quantum computer itself. So pretty much every quantum computer is hybrid at some level. So being it at the control system or decoders. So we have lots of integration with HPC just in the workings of the system itself.
Yeah, I'll continue from there. Yes, we have a similar view, I think, of the world of that. I think, you know, as stated sort of earlier on today, we're in this NISQ era. We don't have fault-tolerant machines, so you're really limited ultimately in the circuit depth you're going to be able to run. So there's things, if you can sensibly do them on you know, a classical computer, so if you can run your optimizer on a classical computer, we can start looking at interesting ways in which quantum computers sort of could be used. And I think that allows some early adoption, or at least some early trials in areas that we would otherwise perhaps be waiting longer for if it was purely, well, not purely a quantum solution, but more heavily sort of quantum. So something we're looking at a lot at. We've partnered with companies like NVIDIA on this and develop into the CUDA quantum framework, where you've got this unified programming approach, and we can start playing with it effectively. So alongside that, we then try and bring some of that HPC infrastructure into our environments as well. So we have, for example, NVIDIA Grace hoppers that we try and put right next to the QPUs. We like to think about this as R&D because it's it's not something that we've necessarily come to the sort of final conclusion as to how it will look, but it's good experimentation to be doing this in our view.
I think that we have to recognize that quantum computers are going to be immensely powerful for a subset of problems.
Yeah.
I would not want to use a quantum computer as a calculator.
Yeah.
And a lot of the problems that we care about and that we highlight as the future applications for quantum computers. I mean, if we think about a large complex molecule like a protein, the areas of the types of problems that we are trying to solve today that can be accelerated with quantum computers, I think is still unknown, but it's likely to be some subroutines that are the core of the very difficult part for classical computers to solve that will be transferred to a quantum computer. So I think that co-designing the application with the implementation and orchestration between different types of classical and quantum resources is really important. I think that we need to think as quantum computers, at least in the early stages, but very likely for a very long time, as co-processors in a hybrid HPC environment. And I think that we've seen some early examples of that, but there is still a lot more work that we need to do by having access to quantum computers and really understanding what are the things that they can do for us, because even trying to model them mathematically is incredibly hard, right? So there will be a lot of back and forth between how do we really isolate that kernel that should be run on a quantum computer rather than be running on a cluster of GPUs and so on. So for us, the way that we think about hybrid computing has all the different phases that were already mentioned. I mean, we're looking at from the application level, how do we orchestrate, how do we break things down? We're looking also at, for example, using decoders that we've done some work together with NVIDIA showing that decoders that are using machine learning tools can have the same efficiency as some of the kind of leading decoders like maximum likelihood estimation, but with up to a 50x increase in speed. And thinking now about how the classical part can help quantum computers, we can use, if we have these things co-located, we can use the classical infrastructure to continuously improve the performance of the quantum computer by using all of the tools that we've developed for machine learning, for artificial intelligence, and bring that into the operation of the quantum computer. I think that is very important, and I think that leveraging that technology is going to make the whole field move a lot faster.
Yeah, I think this sort of side topic could have its own panel discussion, but we saw earlier from the McKinsey report, still a significant portion of funding for quantum comes from federal funding, from state level funding, and there is sort of this need of translating to the public what the expectations are. You're not going to have your personal quantum computer in your living room. It solves a very specific problem set, and there will always be some sort of space where, from just like a job scheduling standpoint, you would never want to use a quantum computer for that would be a very expensive calculator to run. And so maybe if you could all just touch a little bit on at these early stages, because our technologies take so long to develop in the roadmaps, but we're sort of tethered to public funding. How should we be messaging sort of the promise of without overhyping it? How can we say, hey, we're being good stewards of this funding you're getting, and we're taking this step-by-step approach?
From my point of view, we always need to just be very clear about what quantum computers can do and what they cannot do. And I think that, I just want to address the point of hype. I think it is not helpful for anyone to make outrageous claims about what can be done today or next year, because that is the kind of thing that erodes public trust, right? If the messages that the public is getting is, oh, quantum computing is 1 year away from transforming your daily life, and that 1 year away keeps happening like for 20 years, then we're just not going to see the kind of continued support that we need. I think that at least the way that we approach this is by focusing on the promise and what we know, what we don't know, creating excitement in the public, and trying to draw a kind of what is the path to that, right? So I think that, regardless of whether you're ever going to have a quantum computer in your house, thinking about the kinds of industrial applications that we heard about in the earlier session from McKinsey, I think that is really important.
Yeah.
And tying that to the types of technology roadmaps that are presented by the companies and saying, hey, here is our expected time at which it will start being applicable to pharmaceuticals, to new catalysts, to even financial sector, but then kind of starting to bring that back. And I think that today even there are some really interesting things that we can do, maybe not there, but in scientific discovery. I think that the early uses of most technologies are actually for science.
Yeah.
And today we are seeing that. And I'm not talking just the science of quantum computing, right? Like recursive, like quantum computers for quantum computers. But I mean, some of the work that we've done with a type of system that I didn't describe here, but using analog quantum computers, is simulating physical processes for which, the public spending in HPC compute, for example, at the Lawrence Berkeley National Lab has the NERSC supercomputer. That public spending is real, and it can be complemented by what we can learn from these quantum simulators in problems in condensed matter physics and high energy, the kinds of things that we heard about CERN. I think that these are the early use cases where there's a very natural mapping of quantum to quantum, where we can see early advantage, even if it doesn't have a huge commercial value right now, but we have seen over and over again that developing new and better science later on leads to new and better applications.
Great. Yes, Stephan.
Just a thought that I have often in this discussion in our ecosystem, that I think we make a mistake, right? We always think about how to explain to the broader public what quantum computing is and what it can achieve. But I'm not sure if the broader public really understand what high performance computing is and what it is needed for and does. And I think for the foreseeable future, these two things will go together. And we might think about combining this education piece.
Yeah. But I think that focusing on the application here is really what matters, right? Because maybe it's not good to admit ignorance in a panel, but I don't think that I could describe how my laptop works at every level of abstraction. So I don't think that the general public really needs to understand what is a qubit. And I could go on and on about SU2 symmetries and so on, but that's not really what matters. What matters is, can you do something useful with it? And I think that's why we need to start with that future promise of what is the application, whether it's for you personally, because you're running these things, or because new pharmaceuticals are coming out faster and cheaper. I think that that's where we need to anchor the discussion.
Yeah, 100%. I think just early this week at World of Quantum Munich, a constant theme UN was there, large corporations were there. The common theme was education on sort of how will it change the day-to-day person's life who doesn't have a PhD in quantum physics? How do we improve accessibility to the technology? How can we lower the barriers that to really use the benefits of what quantum computing promises? You don't need a PhD in quantum computing. And then at some stage, you may not even need to know how to program a quantum circuit. You can just go straight to the application that you're trying to solve. And if you then expose it instead of a few brilliant minds to orders of magnitude more brilliant minds that can access it, then you get into the exciting part of the problem solving piece. So for kind of our, as we head towards the end here, wanted to hear from each one of you, whether we're at the QP level or as we start to scale into these first generation of what would be an eventual quantum data center, what should we be thinking about in terms of interoperability, even amongst ourselves as sort of as a quantum company to another quantum company, but also as we start to integrating with these very large, largely classical data center infrastructures. Again, Owen, you talked about, we all have to pay a water bill and an electricity bill. We have to cool something. We have to like have lights in the building. We're just a little bit more sensitive to how those things work. So interoperability is going to be key in how we do that at all scales. What are your sort of thoughts on that?
Yeah, well, I think first thing I would say is that maybe the quantum computing community needs to look a little bit closer at what's already been done.
Yeah.
There's lots of discussions over sort of quantum data centers as though we've got to reimagine everything that's been done before. The HPC world's been there. We had a talk this morning about how the semiconductor industry has transformed things. We don't, we can rely on many things that have been developed by, very clever people honed over a long period of time. So I personally would like to see the discussions move more into, an understanding about what exists already and why it may not be fit for purpose and how it needs to be adapted, rather than we're going to come in and define for everyone else in the compute space how it's all going to work. And I think that sort of lends itself actually to the previous discussion over, what are we building here? We're building, accelerators that are going to be good at some particular forms of problems. They're not going to replace general compute, at least not in the next, 10 to 20 years. So I think that's the more realistic sort of approach to, how we should be looking at things. I think the standardization is another great one. There's some good work being done at the moment on data center readiness and what it actually means for data centers to be able to adopt quantum computers into their environments, the things they have to be educated on. So there's those sorts of levels of conversations that need to be had. And then I think there's lots on standardization. I think the quantum computing community was really very, very early on that. And we had the mention earlier about things like QuEra. So good work by the QuEra Alliance to get that off the ground, but it's just one of maybe a few hundreds of different standards that we need to develop. And we need to get people behind, and they need to be usable, and they need to be kept alive. So that's at a software level, that's at a hardware level. It helps the supply chain as well. We've got to make sure that we can provide those standards to others in the supply chain and the data centers. I think it's very exciting. Obviously, there's a lot of work to do. Yeah.
Great. Josh?
Yeah, I would just say, I think one thing that could be really helpful is just education. I think, we work to make our systems rugged and to fit within data center constraints, but having people in a classical data center familiar with cryogenics would be helpful, right? So that's not like a completely new concept to them, or vibration specs. So just things that maybe are unique to quantum computers that we certainly are working on reducing those specs, but maybe just a basic education in what is required or what we might be coming in with that wouldn't have been familiar to them previously.
Yeah, I guess it helps with things like remote hands as well. If you're going to, in a world in which this stuff is more distributed, and you have maybe that will happen eventually because people will be worried about data sovereignty and they want to zone like the rest of compute does. You'll need to do these kinds of things, in which case you're going to have remote hands that are able to, identify, operate, maintain these systems as well. So I really agree on the education bit.
Stephan, did you?
No, I just want to maybe come back
Sure.
on two things. Is on the semiconductor industry, touching what we heard in the morning from Hermann, right? This is happening at least now with us, and as we are working with the whole ecosystem. That's how in the 70s, 80s, and 90s, still to this day, semiconductor industry accelerated many developments, and like the latest thing is now coming from it is AI. Is up to a certain level, competitors via the semiconductor people work in a form together, right? Basic processes, unit processes, things like that. It is just so expensive that not every else you would have to have a fab for each customer, right? That's not possible. So there is some sharing, and then comes the level there is no sharing anymore. and the semiconductor industry has learned that over time, how to handle that and respect that and isolate then the customer's IP. And there is a lot of acceleration really from that. There is giving and taking, and it works out quite well. And now we come to the point with these more complex chips, like for example, we saw on your roadmap, it get much more complex on the right side, right? The left side everything can be layouted, designed, and everything by hand, right? Now we are talking more and more and bringing this from our analog chips business, design generators, design automation, all these things will be needed because not a single brain can have the perfect chip in the end. Maybe at the very high end, it will always be a lot of manual work added onto the automation. But like for the academia, getting also better, more complex chips, design automation and generators will help.
I think that going back to a point that we mentioned earlier about the race to just get to capabilities, interoperability is really important, but in a way comes second to that.
Yeah.
And I think that we have really big challenges ahead of us, just trying to get the technology to work.
That first step, yeah.
Yeah, so I think I mean, there's different ways in which we can think about interoperability, and one of them is between different types of processors. I think that is a kind of, it's like a cubically hard problem. You have what is your one type of processor, your other type of processor, and then the connection. And we don't know how things are going to change in that sense. So I think that when thinking about interoperability, I think that it's important to focus on building the right layers of abstraction. And to your point, like there's some things that are shared, some things that are not.
Yeah.
Let's build those abstraction layers that are shared, and let's focus on interoperability with the classical components of the kind of hybrid HPC center, so that it doesn't matter which QPU you end up buying, there is that high level of abstraction that allows for communication and distribution of tasks to that QPU, regardless of what the underlying physical structure is.
Yeah, and I think all of those things merge together pretty well for I think this sets well for the discussions we're going to have for the rest of this afternoon. One last thing before we head into Q&A. What's the one thing from each one of your respective organizations that would most help you reach data center scale? We know utility is sort of the cost of admission. Beyond that, what's the one thing from each one of your companies for us to achieve data center scale?
Maybe I can go first.
Yeah,
I think one thing that's actually goes back to a little bit of an education piece there is, actually data centers are, they're not new, they exist. We've got, high bandwidth connections there. We've got more, storage and storage for data than we could possibly, need at the moment. A lot of great technologies there. I think one of the barriers that we see is how do we get people to a point where they're actually able to use this? And I think it's an educational piece. We have few people in the world right now who can really make use of quantum computers. They are having to program at that gate level, circuit level. The more that we're able to create the right sort of building blocks that help people start with this, reduce that need to know so much about the systems and which parts of the systems work better and how to diagnose them, the more we'll be able to expand the user base. And I think that will help drive the ecosystem a little bit better than sort of the current state of play.
Yeah. Make it more accessible to the user base. Joshua,
yeah, I guess I can't point to one thing, to be honest with you. I think it's a lot of things that we're, it's sticking to our roadmap, building that first system. And I think the other big one is growing the ecosystem. I agree that right now, we have customers, but we're creating new customers as well. So having to do education along with the growth of our systems.
Okay, Stephan?
Yeah, we help our customer partners get both to
the best of both for
to the first machine, and then the easier part is to provide what they need for the 1000th machine.
Long-term partnerships. Alex, I'll give you the last word.
I go back to applications. I mean, so I think that there's a kind of like low-hanging fruit like type of answer to your question. It's developing that communication and orchestration with a classical compute. I mean, we're already doing that. That is really what it takes to start building a data center. But the data center will not be attractive until we have the right partners that have an interest in developing specific applications that can be accelerated by quantum computing. So, I mean, it's very similar to what you just heard from the rest of the panel. It's really about working with the end users who will be materially affected by having access to these quantum computers. I think that is really the thing that we need to focus on, to integrate with the rest of the HPC center in a meaningful way.
Yeah, so the end user may not care that it's from a data center or not. They're just, can you solve my problem? And whatever you think is the way to do it, then tell me what I need to do, right? Great. Well, thank you so much. I want to give a round of applause to our speakers, and then we'll have a few minutes for Q&A. All right, we have time for a couple of questions. Anybody? Yeah, go ahead.
Roger McKinley from UKRI. I should stress I'm arm's length from a government, so my views are my own, not policy.
Not yet, anyway.
An observation and then an unfair question, okay? The observation is this. It was very interesting hearing the discussion on how we're going to persuade our citizens that this is worthwhile. Now, this is fundamentally, personal view, what the missions in the UK strategy are. They are statements which help ministers justify to citizens why spending the money is a good thing. On computing, and they were well researched, we actually didn't need to say what it was for. We just said it's going to be a big computer with 1 trillion operations, and that's good enough. On networks, we said it was a critical piece of infrastructure, and that was good enough. On sensing for health, we had to be more specific. We say we're going to shorter NHS queues from better diagnostics, okay? So we've actually thought this through. Those are citizen and minister-facing statements, and they work. You heard from Tiana. We've managed to get through the internal wrangling of getting money announced. So those work. What's that 600+ million going to be spent on? Well, increasingly, it's procurement. And that's what we've been doing with the testbed program, and my organization's been doing that procurement. And so this money is going to go to buying quantum computers. Now, we are doing business with quite a few quantum computer companies, and at the moment, we're very impressed, but you're late on your promises, all right? So my question, which is totally unfair, is do you think you're doing enough to grow up commercially and become big grown-up companies which deliver what they promise, rather than just looking like labs producing interesting technology? What's your commercial maturity roadmap?
Gauntlet has been thrown. So
Maybe I'll take the first swipe at that one. So I think I'll go back to the applications. So I think the applications need to be more central in driving things through. Those are the things that people really understand. That's where it's going to become tangibly useful. That's the level of the discussion. We do not need to be educating people on, qubits or types of noise. That's our problem, not anybody else's problem. I think maybe something that's come along with some of the industry hype is that it's underplayed just how challenging this stuff is. And, perhaps the hype has actually created a problem for, a barrier, even a separation between, the taxpayers, the sort of industry who want to use this stuff commercially, and ourselves, because it's implied that this is a lot easier than it really is. There's a lot of fundamental new science being developed alongside that commercialization that you just can't shortcut. We're going to have to deal with these challenges. It is very much a moonshot in my view of, it possibly harder because you've got a lot of fundamental physics happening alongside the engineering as well to make this all work. So yeah, perhaps the hype has created some problems is partly my answer there.
I will say that that's one of the benefits that we have is that we spun out of Honeywell. So we have a lot of that rigor already in place. So we have a very large PMO office in our group. So I would say that the timelines we put out on our roadmap that we put out for delivery of our products, we meet. So, but I think that comes from, we have a startup mentality, but we also have the backing of a very rigorous aerospace company that we partner with. So.
I think that I will answer the question, but first I want to, your prelude to the question about what needs to be told to the public and how it has worked with computing and networking. I think, you know this better than probably anyone here in the room, what works, what doesn't work. I think that the way that I think about what we need to tell the public is influenced by how does the public perceive the value of the technology already. I know what a computer can do for me. I know how a computer exists in modern infrastructure, even if I have no idea of how the computer works. So if you tell me your next computer is going to be twice better, right? Twice more powerful, faster, whatever. You can tell me that about my phone. I have no idea how my phone works. But if you tell me it's going to have twice the memory and it's going to have, network connectivity that is going to be twice as fast, that's great. I don't need to know the application because I already have an application in mind. But if you had told me 6 years ago, oh, I'm working on a large language model that has twice as many parameters as the previous one, okay. Good. I have no idea what a large language model is. I only know that now because I have seen the applications. So when someone tells me the next large language model in 8 months is going to be twice as powerful, I know that basically I am talking to a more intelligent, artificial intelligence that can help me in my workflow, making decisions, organizing my life, etc. So I don't need to know the underlying technology. I think that the problem with quantum computing is that if we think about it as just more compute, we are starting to push ourselves into a corner where it's not just more compute, it's different compute in a way that we have never seen before. A GPU, from my super high level of abstraction, a GPU is no different than following a simple set of instructions on pen and paper. The quantum computer is the first ever computer that we are building that has a different set of rules. So what will it be applied for? I think that is really important. Sorry, I'm proselytizing on my personal views about how to handle this conversation with the public. But in terms of the commercial maturity, I think that there's a lot to be said about the value of the technology today versus in 2 years and how quickly it's advancing. and working together between funding agencies and companies, because I think that there's many constraints that are imposed on companies by the fact that the workforce is very small. The kinds of people that have the skills and knowledge to build a quantum computer that will work reliably is really only now starting to form. So a small change in that workforce or a small change in the supply chain, as we were talking about, there are effectively singular points of failure right now, and with the complexity of the globalization of that supply chain and changing political landscapes, that can wildly alter the timescale to produce a system today. I mean, I can speak about our company. We are building that internal workforce. We are standardizing our own internal product so that we can outsource to manufacturing through multiple partners to reduce those singular points of failure. But I think that it's also a question about what is the timeline to deliver on, for example, a full quantum computing system, and what is driving that timeline? Is that timeline driven by a discussion that is being held between the funding agencies and the companies, or is it being driven by other external factors that are coming from just the funding agency and then passed down to the hardware developers? And I think that makes a very big difference. But if we create this dialogue and we agree on what is most important, is it the delivery of a specific set of requirements in the way that we would with a mature technology, or is it advancing a larger vision of driving forward capabilities and creating a healthy economic development ecosystem? I think that we can do much better.
Sure. So we have to break for lunch. So Stephan, make your comment.
3-sentence answer.
Yes, he has a 3-sentence answer. Yeah.
What you wanted, it's happening. Right? We see that our partner customers are going up. The requests they have are now more on point. In the beginning, they were either very unambitious or they were straight out crazy. This has converged. For me, that's a sign of growing up. Of course, there will always be outliers.
So we're going to break for lunch again. Thanks again, our panel. Please talk to them during lunch. Thank you.